Hello, everyone, and welcome to today's webinar, Time-Resolved STED Microscopy. I'm Christy Jewell of Labyrinth, and I'll be your moderator for today's event. Today's educational web seminar is brought to you by Labyrinth and sponsored by Leica Microsystems. For more information on our sponsor, please visit leica-microsystems.com. Now let's get started. I would like to remind everyone that today's event is interactive, and we encourage you to participate by submitting as many questions as you like at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. If you have any trouble seeing or hearing the presentation, you can click on the Support tab or report your problem by using the Ask a Question box on the far left side of your screen. You can also share this webinar on your personal social media. Just click on the Social Sharing tab and let your friends and colleagues know about today's live event. Additionally, today's presentation is educational and thus offers continuing education credits. After viewing the presentation, just click on the Continuing Education Credits tab and follow the process to obtain your credits. And now to our speaker. Presenting live from Genoa, Italy, I would like to introduce Dr. Giuseppe Vicidomini, Senior Researcher Tenured Principal Investigator at the Italian Institute of Technology. For a complete biography on Dr. Vicidomini, please visit the Biography tab at the top of your screen. Dr. Vicidomini, welcome. You may now begin your presentation.
Good morning or good afternoon, depending where are you. I'm Giuseppe Vicidomini from the PI of the Molecular Microscopy and Spectroscopy Laboratory at the Istituto Italiano di Tecnologia in Genoa. And today I would like to talk about time-resolved STED microscopy. I'm really grateful to people from Leica and also to Christy to give me this opportunity to talk about this topic, because this topic represents somehow the last almost 10 years of my research into the STED microscopy. I'm from the ground. I'm a computer scientist, and 10 years ago I just finished my Ph.D. thesis, and I started to move in the lab of Stefan W. And at that time, I don't be so much keen into microscopy. I was mainly working in image microscopy. And when I read this sentence in a review, I was quite surprised. So when I read that more than 80% of the image of a cell in a textbook or in a journal, in a scientific journal, are usually acquired with the fluorescent microscope, I was really, really astonished. But slowly I understand really the reason why not that. And just briefly, most of you maybe already know, but I want to recap the main reason of this great success of optical microscopy, and in particular of fluorescent microscopy. So clearly one of the most important features of fluorescent microscopy, its ability to observe life. So it can be used for recording live cell, live tissue, up to organism. Because since we are using light, and light is not so much perturbative, at least when we are using a low dose of light, it's extremely powerful technique to really understand deeply all phenomena of life. Another very important characteristic, especially for people that work in computer science, is that a microscopy provides you so many information because it's a multidimensionality technique. So maybe the most classical multidimensionality is the fact that a microscope can provide you three-dimensional imaging. So it's not only provide you flat measurement, but we know that life occurs in 3D, and microscopy can investigate 3D phenomena. Then microscopy can be combined somehow with spectroscopy. A classic example is again multicolor imaging. You can label different structure inside your sample, like in this example in which you have actin, mitochondria, and nucleus stained with different color, with this molecule, with this fluorophore, to really understand the cooperation between them. between the different biomolecules inside the system, inside the sample that you want to investigate. And another extremely important dimension in microscopy is the time. So since microscopy is a non-invasive technique, I can observe my biological sample across the time. Another extremely important characteristics of fluorescent microscopy is that it's a very versatile technique. So the complexity of the system is not so huge, and most important, the sample preparation is relatively easy. And when you sit in front of the microscope, probably in a couple of days, you will be autonomous and you can perform your measurement. And then clearly is a sort of artifact-free system. You immediately get out the image that you need and you can analyze it. Another important property is the spatial resolution. So with an optical microscope, you have decent resolution to investigate the most puzzling phenomena of life. But if I ask you, it's really enough, this resolution, the resolution of a conventional optical microscope, a conventional confocal microscope, is really enough to answer to all your bio question. I guess that the answer we know, since we are in the era of super resolution, is that no, clearly no, because let's say the diffraction barrier, this physical phenomenon, doesn't allow you to distinguish features to have a resolution, a spatial resolution, that is roughly 200 nanometers. That depends by the wavelength of light that you are using and by the numerical objective that you are using. In particular, is lambda over 2NA, when NA is the numerical aperture of the objective lenses. But if I have to just say number, since we are using visible wavelength, and anyway the numerical aperture of your objective lens is limited, then this value is around 200 nanometers. But most of the important phenomena occur at a much smaller level, at the molecular level. Most of your macromolecule that you are interested in, your NA or other protein or other molecular machine, are much below this 200 nanometers. So it's clear that if an optical microscope with all the properties that I told you before, the possibility to investigate life, the multidimensionality, the versatility, can be somehow modified in order to improve the resolution below this diffraction limit, this 200 nanometers, you will get enormous benefit. Somehow what I like is to get the same characteristic of an optical microscope, but to reach almost the resolution of an electron microscope. So nowadays we know that thanks to these three gentlemen, Eric Betzig, Stefan L, and William Warner, now we can achieve such molecular scale resolution thanks to the super resolution technique or nanoscopy technique. So now we have access to the scale that previously was achievable only by electron microscopy, but still preserving all the features of a fluorescent or optical microscope, or at least most of these features. And during this talk, I will show also some trick how to effectively preserve this kind of feature, especially the possibility to do live imaging. Okay, probably the first and one of the most powerful super resolution technique that nowadays we can find in many laboratories and can be readily used to the biological community is STED microscopy. So STED microscopy was invented in 1994, and clearly nowadays most of the, as I told you before, most of the lab was invented by Stefan L, and most of the lab has this microscopy technique on board. So the topic of this talk is about STED microscopy. So I would like to take first the chance to introduce this technique. But to introduce this technique, I need before to introduce some basic concept of fluorescence that maybe most of you already know. But just to cover the majority of the audience, I would like to recap at least the basic knowledge of fluorescence. So you perfectly know that fluorescence is the phenomenon by which if I radiate a molecule, a fluorophore, with a specific wavelength, the molecule will emit after almost simultaneously another light with a slightly different color. So that's more or less what we know about what is the basic knowledge of fluorescence. But let's go a little bit deeper, and in particular, let's understand the temporal characteristic of the fluorescence. So the first thing the first step in the fluorescence process is the absorption of a molecule of a particular photon. So here I depicted the molecule in a two-state as a two-state system, and here there is the Jablonski diagram representation. So when the molecule naturally is in the ground state at 0, then it can, if we shine light on it of a particular wavelength, and the wavelength depends by its absorption spectrum that is depicted here, then the molecule, what it's doing is absorbing this photon in a very, very fast manner in the order of femtoseconds, and then move to higher excited state, S1. When is this higher excited state, then it will stay in the higher vibrational states of the excited state for a very short period in the order of picosecond, and then we relax to the lower level of the vibrational states. After spending, and that's a very important property, few nanoseconds into the excited state, and that's what we call the excited state lifetime of the molecule, it will emit a photon with a different wavelength in the emission band of my fluorophore, and in particular the wavelength of emission will be shifted towards longer wavelength because there is a loss of energy. And important, this transition will occur again at the femtosecond scale. But what is very important is that the lifetime of the molecule into the excited state is in the order of nanoseconds. So another important things that we have to know to understand stimulated emission is to understand stimulated emission microscopy is exactly the stimulated emission phenomenon. So in physics, we know that when there is a phenomenon, usually there is always a contrary phenomenon. So if it's possible to excite the molecule by light, it's also possible to de-excite the same molecule by light. And that's exactly the stimulated emission process. So what does it mean? That when the molecule is into the excited states, it's possible to use another photon, in this case it's a red-shifted photon with respect to the emission of the fluorophore, to excite the fluorophore from the excited state to the ground state. In this case, what will happen is that we will use another photon that from now we will call stimulated emission photon to excite the molecule from the excited state to the ground state. And what will happen that we will have a second photon identical to the stimulated emission photon, because we need to release energy from the molecule. So, but it's clear that this second photon is identical to the photon that we used to induce stimulated emission, and in particular it has the very same wavelength. So this means that we can easily select the spontaneous emission, the fluorescent emission depicted here in green, from the stimulated emission that will have a red color. We'll have a color identical to the laser, to the light that we will use to induce stimulated emission. So now that we have clearly in mind the phenomena of fluorescence, the temporal scale of this phenomena, and the fact that it's possible to excite a molecule, but also to excite a molecule by light, so let's try to understand stimulated emission depression microscopy. So to understand the principle of stimulated emission depression microscopy, it's important to understand which is the problem of diffraction in a conventional confocal microscope. So let's take this as a phantom example. So here we have the logo of our institute, the IIT. The dot represents the molecule in my sample. So if we use a laser and we shine this laser, we focus the laser by the objective lens in a particular position of my sample, what will happen that all the molecules inside the sample will be excited, and what will happen is that almost instantaneously, after a few nanoseconds, because I told you that the excited state lifetime of the molecule is the order of nanoseconds, they will emit fluorescence photon. This fluorescent photon is collected by the same objective lens and is imaged onto the detector that is recording a single intensity value that is then stored into the computer. But what is very important, that since light from the molecule is emitted simultaneously, all the light from this molecule will be recorded simultaneously. Thereby, all these molecules inside the excitation volume, and now I depicted them in yellow to represent the excitation step, they will emit light simultaneously, and they fuse all together then signal. So there is no way to separate the molecule in the dot of the E from the other molecule in the other part of my phantom. Since we are in a scanning microscope, what will happen then is that we will shift our excitation volume to another region, and we will record again the fluorescence light. It's very important that we are recording, in this case, the fluorescence that is in a green regime. If we scan across all the sample, we end up in a digital images that is here on the right side, which is a blur representation of my real object. Simply because when I shine light in a region of my sample that, as I told you, due to the diffraction is in the range of 200 nanometers, all the molecules within these 200 nanometers, we shine light simultaneously that is recorded by the detector, and then scanning the beam across the sample, I will form the images. Thereby, there will be no way to separate the light that is coming from molecules that are closer than the diffraction limit, that are closer than this 200 nanometers. Here it's a real example, while this one is a phantom. That's a real example, again, not of a sort of phantom sample, because these are 40 nanometer fluorescent beads. As you can see, it's a blurred version of these beads. But let's see now, as I told you before, now what is the major problem is that all the molecules shine light simultaneously. But if you remember at the beginning, I told you that there is a way to silence a molecule, to some way to prevent a molecule to emit fluorescent, to emit a spontaneous photon, and thereby to quench the molecule, to silence the molecule, to switch off a molecule. That is by stimulated emission. So by stimulated emission, I have a way that I can somehow switch on a molecule and prevent to emit fluorescence. That's not enough to get super resolution, and in particular to get super resolution by stimulated emission detection microscopy. So what I have to do further is to switch off the molecule in a particular position, in a particular spatial position. So as you can see here, so what I have to do, I don't have to switch off the fluorophore everywhere, but I have to switch off the fluorophore only in the periphery of my excitation volume. And to do that, I have to engineering my laser, the focus of the laser that is used to quench, to silence the fluorophore. So now I will call this laser STED beam. And to switch off the fluorophore only in the periphery, I have to engineering the STED beam as a donut shape, with a zero intensity point to the middle and high intensity at STED intensity into the periphery. If I'm able to do this trick, what will happen is that I will only make fluorescence the molecules that are in the center of the excitation volume, while all the other molecules in the periphery will be switched off. As you can see, for example, from this graph. So from this picture, again, after scanning the beam across the sample, I will end up with any digital images that with an improved resolution. As you can see, compare these two pictures. Just because I was able to quench the fluorescent molecule into the periphery of my excitation volume of the scanning microscope. But it's clear that diffraction is still there, so that means that the shape of my donut STED beam is still ruled by diffraction, and thereby I cannot, let's say, make a node that is very small in order to quench all the molecules in the periphery and heavy fluorescent only the one in the very center. But what I can do is to saturate the stimulated emission transition. So what does it mean? I can increase the intensity of the STED beam in order to have enough intensity also very close to the zero intensity point of my STED beam, and this means in the very center of my excitation volume, in order to quench even more the molecule in the periphery. Here, on this side, you can see the graph of what we call the depletion curve that tell you the probability of fluorescence as a function of the intensity of the STED beam. Higher is the intensity of the STED beam, lower is the probability that the molecule fluoresces, that the molecule decay by spontaneous emission. Very important, the molecule is still, after being excited and after see a stimulating photon, will emit a photon. But this photon has the very same wavelength of the stimulated emission photon. Thereby, if we use a proper filter that selects the light only in this region, we can collect only the spontaneous emission, the fluorescence, and discard the stimulated emission, stimulated photon. So if we increase even more, so what we left, the intensity of the STED beam, so now only the molecule that is in the very center of the STED beam can emit photon, while all the other ones are switched off. So that means that in a STED microscope, what we can do, we can tune the resolution of my microscope by simply increasing the intensity of the STED beam, and we'll follow these rules. So we have a new terms in our resolution, and in particular in the size of detection volume, that depend by the intensity of the STED beam. Higher is the intensity of the STED beam, higher is the resolution of my system. As you can see from this phantom example, in which now it's clearly visible that these are two nanoparticles instead of an elongated one. So STED microscopy, this means that STED microscopy can provide you higher intensity, higher is the STED beam. So by taking advantage of stimulated emission, but also of the saturation of the process. So we can increase the STED beam in order to having fluorescence only into the very center of my excitation volume. So we reduce the effective fluorescent volume of the microscope. And then scanning this effective fluorescent volume across the sample, we can end up with a high resolution image. That in principle is unlimited. By increasing the STED beam, I can reach higher resolution. So that's enough. Let's say theoretically that's enough, but practically there are some rules that we have to follow. First, an important rule that we have to follow is that we have to preserve some spatial conditions. So we have to be sure that our STED beam is perfectly overlapped with our excitation beam. Another important property that we have to respect to have properly high resolution imaging is to preserve the spectral condition. This means that the STED beam wavelength has to be selected in order to effectively induce stimulating emission, not other process. Let's go a little bit deeper into this. So we know we represented the molecule in a very easy way with a two-state system, but unfortunately the system is much complex. So, and what can happen is the STED beam is not only inducing stimulated emission, but what happens is that may induce higher excitation. So move the molecule from the ground state, for example, from an excited state to an even higher excited state, or if the molecule go to a triple state to even higher triple state. So, and unfortunately these states are prone to be bleached. So that clearly is something that we don't want. So how we can circumvent this problem? So if we know not only the absorption, emission, and the absorption of the molecule, spectra of the molecule, but also the emission spectra of the molecule, and also the transit state absorption of the molecule, we can move out from the region where the molecule absorbs when it's into excited state, like in this case for the GFP, which we move from 592 nanometers to 566, and thereby avoiding the absorption from one of these states. So, but when we move our wavelength of the STED beam, we have also to consider that if we move, if we redshift the STED beam, what will happen is that we reduce the stimulated emission cross-section. So we need more power to, more intensity to effectively quench the fluorophore. On the other side, if we blue shift the STED beam, so in the direction of the emission of the molecule, what will happen is that there is the chance that we also excite the molecule. We don't induce stimulated emission, but what we induce is a direct excitation from the STED beam, as depicted in the Diabrowski diagram. So there is a solution for that we call STED microscopy. I will go fast on this part because it's more important than the other part of the talk. As I told you, what can happen is that if the STED beam is too close to the emission spectra, like in this case, it will directly excite the molecule, the fluorophore. So as you can see here, for example, that's a confocal image of my phantom, 40 nanometer beam. That's the image when I switch on the STED beam, so I expect it to increase the resolution. And effectively, you see an increase in the resolution, but at the same time, you see also very blurred background that also hidden the structure of your sample. But since this excitation, this fluorescence induced by the STED beam, I can apply my lock-in detection technique to subtract such a background. And that's exactly what happened in this scheme of this architecture. So if I'm able to implement this lock-in detection, I can remove the background induced by the STED beam and end up with a very clear and sharp STED images. So I can partially solve the problem of the background induced by the STED beam, what we call also anti-Stokes emission background. So here is just a recap of all the literature on this topic, and I suggest you to have a look to this review if you want to go deeper on this, or this very recent review, if you want to go deeper on this topic. Another very important condition to satisfy when performing STED microscopy is the temporal condition. So it's very important that the STED beam photons, the stimulating photon, act when the fluorophore are in the excited state. As I told you, it's very important that since the molecule will stay only few nanoseconds into the excited state before decay, the excited by emitting a photon, if I want to quench, I have to act early. So I have to come with the STED beam much early. So what does it mean this? That the depletion of the fluorescent signal, so how good I'm able to quench the fluorophore, depends by the number of stimulating photons to which the fluorophore is exposed while residing in the single excited state, when it is into the excited state. Since typically fluorophore has in the range of 4 nanosecond, let's say 4 nanosecond excited state lifetime, and the cross-section of the stimulated emission process is relatively low, so we need intensity to, let's say, saturate saturate the stimulated emission process in the range of 10 milliwatts per centimeter square. And if we want to reach the few tens of nanometer resolution, we need to increase even more the intensity up to gigawatts per centimeter square. Such a value is not so high if we compare to two-photon excitation, but it's clearly higher than when we compare to one-photon excitation. So in further, what happens is that to reach such kind of intensity, we need pulse scheme. So we have to excite the molecule with a pulse laser, and we have to deplete as well the molecule with another pulse laser. So we need quite a complex scheme. So to solve this problem, clearly what we can do, we can use long lifetime fluorophore. So that means that now we can, if we are able to increase the lifetime of the molecule, clearly we have more time to induce stimulated emissions, so thereby we can reduce the intensity. But it's not easy to engineering organic fluorophore or protein with such a long lifetime fluorophore. So that's clearly not an easy solution. Another solution is represented by the time gating. So what is time gating? So basically the idea of time gating is that we want to register the fluorescent cilia only after a time Tg, after a fixed time, from the fluorophore excitation event. So we excite the molecule, we wait for a certain time, and then we start to record the fluorescence. In such a way, what will happen is that the signal that we record will come only for fluorophore that have resided to the excited state at least for a time Tg. So that has stimulated photon at least for this time. So we can somehow prolongate the effective lifetime of the fluorophore. So that's the principle of gated STED microscopy. Let's go deeper in this to better understand why we can, let's say, reduce the intensity of the STED beam by using time gating detection. So this figure represents the fluorescence lifetime, represents the temporal response, the temporal behavior of the fluorescence from an excited molecule. So if the molecule is excited at time 0, so it will decay following this sort of exponential function. If we shine also STED light on the same molecule, so what will happen is that the molecule will decay much faster, as you can see from this red light. Higher is the intensity of the STED beam, faster will decay this. Faster will be the decay of the fluorescence. So that simply comes by the fact that now by stimulated emission depletion, we open a new de-excitation pathway on the molecule. And in particular, this means that the lifetime of the molecule will become much shorter. So that's the equation that describes the lifetime of the molecule, that is 1 over the rate of spontaneous emission plus the rate of stimulated emission. Higher is the rate of stimulated emission, faster is the decay. But if you see this graph, you also note that at the time 0, there is almost no difference from the probability, there is no difference in the probability of the molecule to fluorescence. But the probability to fluorescence becomes much more different when the time span across this dimension. So in particular, what will happen that after certain time, there is a huge difference between the absence of stimulated emission or the presence of stimulated emission. So that means that if we record the fluorescence after, for example, a time Tg that is in the order of nanosecond, in this case is 1 nanosecond, now the probability that the molecule fluoresces is much less. The probability that the molecule emits, the probability that we record a fluorescent photon from this molecule will substantially reduce. So as you can see now, our depletion curve will be enhanced. So if we need 80 milliwatt per centimeter square to quench at a few percent, now the molecule, now we need only 40 milliwatt per centimeter square to reduce almost to 0 the probability of fluorescence. So if we even increase more the intensity, if we even increase more the time delay, we improve even further the depletion. So now we have clearly a way to enhance the probability to quench a fluorophore without increasing the intensity of the STED beam. So that's an example on a real sample, that's a nanocrystal. As you can see, by increasing the intensity of the STED beam, what will happen is that we change the lifetime of the molecule, becomes shorter and shorter. But what is more important that if we apply time gating, so for example, we collect the light after 5 nanoseconds, we increase the depletion curve. So we reduce the probability to collect a fluorophore, and thereby we can somehow reduce the intensity of the STED beam. So what does it mean this in terms of resolution? So here now we are back to the conventional scheme of a microscope. So we have a Gaussian excitation and we have our donut STED beam. If we collect the light after a time Tg, what will happen is that the effective fluorescent volume will reduce, as you can see from the red to the green. So one important aspect that now we are dealing also with continuous wave laser for the STED beam. So we are also reducing the complexity of the microscope. So that's an example, again, on a real sample. So that's a single particle, in particular is an empty center. So as you notice, here is the confocal images, that is roughly the 200 nanometer that we expected by diffraction. When we switch on the STED beam, we enhance the resolution, now it's much smaller. And when we apply time gating, so we collect light after a few nanoseconds, in this case after 5 nanoseconds from the excitation event, we further reduce the effective fluorescent volume, and in particular the Poynting factor of the system, and thereby we enhance the resolution by simply play with a time gating, so without increasing the intensity of the STED beam. So that's maybe a recap of what I told you before. So you know that in STED microscopy, as I told you before, we can increase the intensity, we can increase the resolution by increasing the intensity of the STED beam. But now we have a second pathway to increase the resolution of the STED microscope. That is by delay the recording of the fluorescence. It's by implementing time gating. As you can see here, if we maintain the same STED intensity, but we delay the recording, then the resolution improves. Here there is the equation, so now we can improve the resolution by increasing the intensity of the STED beam, or we can increase the resolution by delay the recording of the fluorescence via time gating. So that's an example of this technique on a real sample. So as you notice, the first image is the confocal. Then when we shine the STED beam, then there is an enhancement in resolution, but a further enhancement of resolution is obtained when we apply time gating without increasing the intensity of the STED beam. Here a detail, and you can clearly see how much easy it is to resolve the turbulent structure into the sample. Confocal, continuous with STED, and gated STED. So we can somehow improve the resolution without increasing the STED beam. But what's more important is that we can achieve a certain resolution by using much less power. So we can increase the photostability of our system. So we can reduce the bleaching of our microscope. So that's particularly useful not only in terms of photo bleaching, but also in terms of phototoxicity. So thanks to this time gating implementation, for the first time we can record live cell imaging, like in this example, when you compare confocal to gated STED, and we record the diffusion of GFP labeled vesicles that are moving along an axon of a Drosophila larva. So thanks to Leica and to Sigrid for giving us the opportunity to show this data. I will skip the part of the application of gated into pulse system, but clearly you can get the same benefit also in pulse in pulse STED for the same reason. So what does it mean? That nowadays thanks also to time gating, we can use much less complex laser, such as, for example, the sub-nanosecond fiber laser, instead of very complex architecture like in the early implementation of STED microscopy. This is an example in which, again, we show that that's the confocal. Here is the STED image, again, in a tubulin sample, and that's the improvement that we obtain by using gated STED on a pulse architecture. In a pulse architecture, the main reason to use in a pulse architecture is the fact that now we can, again, reduce the intensity of the STED beam simply because now we can spread the photon across a relative long pulse in the order of, let's say, 1 nanosecond without losing in resolution, but improving the photostability of the fluorophore. Now the bleaching reduces much due to the fact that I can decrease the intensity of the STED beam. Another way to explain gated STED microscopy, to explain why it's important to perform time-resolved STED microscopy, is approaching this from the point of view of the lifetime. So as I told you before, what we have is that when we shine a STED beam on a molecule, we modify the effective excited state of the molecule. And in particular, higher is the intensity of the STED beam, shorter is the lifetime of the molecule. So faster is the emission of the photon of a spontaneous photon of a fluorescence if this occurs. So that means that since our STED beam as a spatial signature, so and in particular the intensity is very high into the crest and is zero into the center, what will happen is that we will induce a spatial signature into the excited state, into the lifetime of the fluorophore. And in particular, what will happen, as you can see here, but also from this graph is that if the molecule is into the center, then it will have a longer lifetime. when the molecule is moving into the periphery, when the molecule is into the periphery of the excitation volume, what will happen is that the lifetime becomes shorter. So molecule into the periphery will be characterized by a shorter lifetime, molecule into the center will be characterized by a longer lifetime. So that means that if we apply time gating, so if we collect fluorescence only after a certain time, so we will collect the fluorescence coming only from the long lifetime molecules. So the molecules that are into the center of the excitation volume. So here it's the same example that I showed before, but depicting also the lifetime of the molecule. So as you can see here, the molecule, when it's into the center of the excitation volume, it has a longer lifetime than the center, so it's roughly 40 nanoseconds. But when it's into the periphery, the lifetime becomes much shorter, goes up to a few hundreds of picoseconds, that is depicted here in blue. So if we apply time gating, so that means that we select the photons that are coming only from the center of the detection volume. But there is a big problem in the time gating implementation. Unfortunately, when we apply time gating, we do not discard only photons that are into the periphery and thereby the photon that effectively we don't want, but also photons that are coming from the center of your constant function of your detection volume of the microscope. So that means that the signal to noise ratio of your image drastically decreases. As you can see here, when we apply time gating, unfortunately, the peak intensity changed from 190 photon counts per fraction of 1/10 of millisecond down to 40, only 40 photons. So that means that if you have a dim sample or if you have a background in your system, then unfortunately you will end up with an image that is pretty noisy, and then you cannot clearly distinguish any feature in that. So how we can solve this problem? So that's why we start to implement not an hardware approach like in the time gating, that is very straightforward approach, but a computational approach that is we call separation by lifetime tuning. So to understand this approach, I need a little bit of math, no, not very complex one, but I need to introduce a couple of functions. So first of all, as I told you before, thanks to the STED, to the stimulated emission phenomena, and to the fact that I'm using a donut-shaped STED beam, I can induce a spatial signature into the lifetime of a molecule. So in particular, if I have a single molecule that is located at the distance r from the center of my detection volume, the fluorescence signal emitted by this molecule can be described by this function. So that is an exponential function in which the rate of the exponential is given by the lifetime of the molecule, and the lifetime of the molecule, as I told you, is modified by the STED beam. So let's assume that, and again, another important thing, that there is a parameter that is given by the excitation of the, where it depends again by the position, and is how strong I excite the molecule. But that's, let's say, is a multiplicative element. Now, let's do one step further. Let's think that we have two molecules, so a different distance from the center. So what will happen to my fluorescence signal recorded by the detection volume is that it's simply represented by the sum of the two fluorescence signals from the two molecules, one in the outer part of the detection volume, the other one in the inner part of the detection volume. Let's make one step further. So let's now assume that we have more than two molecules, and in part, but that we have all the molecules in two concentric rings, one inner ring and another outer ring. So in the reality, this will not happen, but we demonstrate that making this assumption will not change significantly the results without introducing too much complexity in the problem that we will solve. So if we have such a condition, so the fluorescence signal, it can be described by the sum, again, of two components in which we make a further step and we use the normalized exponential function. So we have a first fraction that is given by the photon coming from the inner part of my detection volume, and the second fraction that is coming from the outer part of my detection volume. Very important, these are linear independently. So clearly the problem, what we would like to have to enhance the resolution is to collect only the fluorophore, only the fluorescent signal coming from this part, from the inner molecule. So one can think to make a fitting of this function and extract only this component. But there is a much easy way to do that does not need any modeling of these two functions, does not need to know that these are exponential functions first. So that is to represent this signal into the Phasor plot. So a Phasor plot allows me to take a temporal signal, like in these cases, and to transform in a simple two value, because what we calculate is the cosine and sine transform of my signal. And we end up with a simple two value, with a simple point into the so-called Phasor plot. One of the beauty of the Phasor plot representation is that if we have a linear combination of signal, like in this case, we end up with a superimposition of vector in the Phasor representation. So that means that now my Phasor will be simply the weighted sum of two Phasor, other Phasor points that represent the function of the inner fluorescence and the function representing the outer fluorophore. So this kind of system can be easily inverted in a very fast way by simply solving a two variable linear system. And what we can extract very fast and very easily only the signal coming from the inner part of my detection volume. So that means that compared to the time-gated implementation, we are not discarding photon coming from the center of my detection volume, but we are simply separating this photon in order to generate my high-resolution images. Another very important and nice property of the Phasor plot is that it's able also to take advantage of, that is able to separate the background, for example, the uncorrelated background. For example, the background that is coming from the excitation of the STED beam. Since this background is uncorrelated respect to the variable t, so it's constant respect to the temporal dimension, so what will happen is that it will be represented as a point in the zero, in the center of the polar coordinate. And again, by simply math, we can extract the three components, the inner part, the outer part, and the background, and end up with a system that is with a technique that is able to isolate all the fluorophore coming from the center, and also not induced by the STED beam, and thereby not background photon. So now the question is how we can effectively implement this approach. To effectively implement this approach, what we need simply to know is the Phasor is the Phasor of the inner component and the Phasor of the outer component. But that's relatively easy because the Phasor of the inner component is simply given by the confocal counterpart. And in this case, since in most of the cases a single exponential decay, you will rely into the universal semicircle. That's also important to visualize this graph, because here we show that when we're increasing the intensity of the STED beam, so we move along this direction, you can clearly see that the Phasor plot is moving toward this direction because the lifetime of the molecule becomes much, much, much shorter. So as I told you before, we don't need only the representation of the Phasor for the inner part, but we need also the Phasor for the outer part. In this case, we found out that the best solution is to take as a function corresponding to the Phasor in the outer part, an exponential decay of the molecule into the donut crest. So that means that it is very easy to extract from experiment these two values. When we have these two values, then we can simply decompose for each pixel of our images, the Phasor plot in the two components, and highlight obviously only the inner part. So as you can see, for example, from this example, so here it's again an example of imaging of tubulin in a confocal modality. Here is the Phasor plot representation. That means that for each pixel we calculate the Phasor representation, and it should lie on the semicircle, but since there is a sort of self-quenching, is slightly shifted from the semicircle. But that's the Phasor plot representation of the confocal. So that will be, let's say, the Phasor for our inner photon. When we activate the STED beam, as you can see, there is a huge shift of the Phasor plot that is moving towards the short lifetime, because as I told you, when we induce stimulated emission, we start to shift the molecule towards shorter lifetime, especially the one into the periphery. And also there is a background that is represented by these points, and as you see, the Phasor is also moving toward the background. But what we can do now, by simply solving for each pixel a linear equation, we can separate the photon from the inner part, as you can see here, from the outer part, and from the background. And we end up with a much higher resolution image, in particular when we compare with the gating. As I told you before, the gating is wonderful when you have high signal-to-noise ratio, but such in this case in which we have a pretty strong background, as you can see here, there is no a huge enhancement in resolution. But only when we separate the photon from the inner part, from the outer part, and from the background, we end up with a very high resolution image. So here I just show you how by a computational approach we can get the same benefit of time gating by solving the problem of the signal-to ratio and also by naturally removing the background. So we have another way to increase the resolution of the STED microscope without increasing the intensity of the STED beam, and thereby without increasing the phototoxicity, and make it really suitable for live cell imaging. So again, like for the time negating, this approach, the split approach, can be extended to pulse implementation, also because the beauty of the split approach doesn't need a model. So for example, in the case of pulse STED implementation, we don't have anymore the cake that follows exponential behavior, but we have much more complex function. So with this, I would like to finish, but I would like to thank all my group at the Italian Institute of Technology, and in particular the molecular microscopy group. Further, I would like to thank people from the nanoscopy group, in particular Alberto Diaspro, Paolo Bianchini, and Luca Lanzanò. Luca Lanzanò was the guy that developed with me the split approach, the last part of the talk. Then I would like to talk people from the Polytechnic of Milan for developing spatial detector for the time-gating implementation. Then I don't want to forget the people from my previous group, and in particular from the Max Planck, Thierry Stefanel, Andre Scholle, Gay Monero, Q Hanan. And then Christian Egelin from now at the Oxford University. And finally, a very big thanks to Leica Microsystems that gave me a chance to recap a little bit these 10 years of research. So thanks to all of you for your attention.
Dr. Vicidomini, thank you so much for your informative presentation. That was a lot of information to take in. Now, to our audience, it is now time for our live Q&A. Now, if you have a question you would like to ask, please do so now. Simply type them into the Ask a Question box and click Send. We will answer as many of your questions as we have time for. Now, it looks like we have time for just a few questions. Dr. Vicidomini, let's start with this one. If there is a requirement to increase the power of STED beam for more resolution, then how's the photo bleaching controlled?
Okay, so first, once again, people organize this webinar. And before replying to this question, I just would like to highlight the fact that You can find my email into any slide of my presentation, and I will be happy to get all your questions also by email and reply one by one, and also maybe to chat with you. Concerning the last question, the question that I got it, so clearly photo bleaching is, and not only phototoxicity is one of the big somehow limitation, especially in the early implementation of STED microscopy. So increasing the STED power for sure will increase photo bleaching and phototoxicity. But I want to say that a lot of development here, I just present this time-resolved approach, how to reduce the intensity of the STED beam. So nowadays, there's not really anymore a problem, and STED can be really applied to live cells. So new probe has been developed, new very sensitive detector has been developed, new laser has been developed, and thereby, if 10 years ago, photo bleaching and phototoxicity was a problem instead, now that's not anymore. I hope that I answered to your question.
Very good. Thank you. Our next question. As the STED beam is not perfectly zero in the center, how much shorter do you expect the good fluorescence lifetime to decrease?
Okay, yeah, that's another, let's say, technical aspect. So clearly, ideally, would be great if the density in the zero of the donut is zero, like the name. But that's not happening, especially when you have aberration or we are working in conditions that are far away from optimal, when you go deeper and so on. Again, that's a problem because you quench fluorophore into the center and that you cannot do nothing. It's a problem also for these time-resolved approaches because you change the lifetime also into the center. But for example, in split, you can take into account about this problem into the mode, into the algorithm, and somehow compensate for this aspect. So just to resume, the best will be to remove and to correct for the aberration that reduce your zero intensity quality. But on the other side, by computation, you can somehow overcome also a little bit this problem.
Dr. Vicidomini,
yeah.
How are long lifetime fluorophores produced?
Okay, okay. The dream will be to have a very long lifetime fluorophore, because in this case, let's say the need of intensity, STED intensity will reduce. Clearly, it's possible to engineering and maybe not organic fluorophore for this, but there are some particles, for example, in the center as 10 nanometer lifetime. I know that other nanocrystal can have much longer. But we have to keep in mind that we want to make this technique readily be used for life science. So I guess that at the moment does not make so much sense to develop, to use some probe, to develop some let's say, some inorganic fluorophore that with long lifetime that then you cannot use for really bio application. So that means that organic fluorophore has 4 nanosecond lifetime. That is already pretty good. So I don't think that that's maybe one of the most important direction for the developing STED microscopy. So I think that it's much more important to optimize the current fluorophore to make them more photostable and thereby to react better to more light.
Dr. Vicidomini, how dependent is the split STED effect on the particular dye? And are certain dyes more useful than others?
Okay, so let's say again, longer is the lifetime, better it is. But that's a general technique. So any fluorophore is fine for split STED. The beauty of split STED, that give you a very big enhancement in a region in which you do not use a very high intensity STED beam. So that's the most important part of split STED, I can say.
Thank you, Dr. Vicidomini. Now we have time for one more question, but I do want to remind our audience one more time that
all those questions we are unable to answer today, and any of those questions that come in during the on-demand period, Dr. Vicidomini will be answering those via the email address you provided at the time of registration. Dr. Vicidomini, is split STED particularly good for strong background as compared to time-gated STED?
I think that that's the basic, the most important difference between split STED and gated STED. At least in the version that I show you, split STED it's perfectly able to remove background induced by the STED beam because, as I show you, is a sort of uncorrelated background. That in principle can be also implemented in time-gated STED, but I can say that the results that we see during in our experiences that split STED was better. So as I told you, also time gating can be combined with the convolution and thereby with other methods, with computational methods to make the quality of the image better. So the beauty of split STED is that it's a very straightforward approach. Almost no input from the user are needed, while maybe in the convolution you need a little bit to clear about some parameters. So that's also why I think that Leica, as far as I know, is going also a little bit in this direction, so to implement in the machine similar approaches. So that's why I'm pretty confident that we will, I'm sure that this split STED method will be implemented almost in any microscope. So, and that's why I like also to thank all my collaborator, in particular Luca Lanzano, that is let's say the first author of the paper that introduced the split STED. I can see really a bright future for this implementation.
Dr. Vicidomini, thank you so much for your time today and for your important research. I would also like to thank LabRoots and our sponsor, Leica Microsystems, for underwriting today's educational webcast. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. That's all for now, and we hope to see you again soon. Have a great day.
Have a great day. Bye. Thanks a lot.
Thank you. Bye-bye.